control is a closed loop control action is taken. So based on the change in wind velocity, the required change in the pitch angle is made in an actual wind turbine plant. Here it is done manually, so you may think that it is very easy to do that, but it is not like, actually it does not like happen like that. Any other question, anyone? So can you see my screen?
Yes, sir.
Experiment number 5. Okay, so let us start with this. Outline of this discussion will again start with the resources and introduction, then the technologies related to solar PVs. Broadly, we classify it in 3 generations. So the third generation is still in R&D level, and the first generation is still dominating in the commercial application. Then we will talk about the motivation and objective for this experiment. Then experimental setup video is there. Experimental cases. There are 2 cases. Video recordings are uploaded on Moodle, and based on that, results and discussion and conclusion, and then finally the report format to be done. So just a minute. Let me check whether it is completed on Moodle. It's not yet done. Okay. So all of you can see my PPT screen easily?
Yes, sir.
Good. So today the network is better. Last time it was some problem. I hope the video should also be able to share. So again, I have put 2 NPTEL lectures here, and they both are from same Professor Banerjee, and it has been explained in a very simple and very easy manner. And same book, again chapter number 8 is useful in this topic. Earlier there was another chapter on wind energy system. Now this is on photovoltaic material and electrical characteristics. So please go through this chapter and these video links. It will be more helpful for you to follow it up. Okay, let's talk about generic global scenario of solar PV system. And if you remember the similar profile we have seen for the wind generation also, and that was also around 600 plus, and this is also around 600 plus gigawatt in 2019. Here the addition, you can see it is much more than the addition from the wind. In the addition, per year addition in the wind was around 50 to 60 gigawatt, but here the addition you can see after 2016 is more than 100 gigawatt per year. So wind technology was more early established and matured, but PV technology came up little later and slowly maturing up, slowly adding the capacity, but it has gone very fast in recent few years. You can see the growth is much faster than the wind technology, and the installation capacity has also come around the same 600 gigawatt range. Other reasons are that the cost, the energy cost is reducing very fast for the solar PV, the module cost and the other system component cost. So in India we have tariff has gone down to around 2 rupees per unit, right? And that is significantly high. And our overall capacity in India of solar PV is reaching around 38.2 gigawatt. That is around 10% of total installed capacity. Our total installed capacity of India is around 375 gigawatt. So PV is around 10% of that. Wind is also around 10%. That is around 30 or 40 gigawatt. So in the next experiment, I will show you some Indian power scenario, facts and figures. So that will be help you to understand the situation. Where do we stand on global front, as well as internal our Indian power scenario. What are the fuel mix we are using? What is the contribution of each one of them? So that will be interesting to discuss. Okay, so now we talk about the solar PV cell technologies. As I am telling you, there are 3 generations in which they are classified: first generation, second generation, third generation. First is silicon wafer based technology, which is still dominating in the market. Still we are using monocrystalline, polycrystalline solar cells. So that is a silicon based wafer based technology. Wafer is actually before the cell. The wafer is the semi finished cell basically, or unfinished form of the cell. So whoever is manufacturing the modules in India, solar modules, they are importing the wafer. Either they are importing the wafer or they are importing the cell directly. Then those cells are fitted, and the module is manufactured. So all these cells are series connected, and they are encapsulated within the glass and substrate, and the metal framing is made. So basically the module is made. And if they import the wafer, then the processing on the wafer is made to make it cell. So there are 4 or 5 stages are there, from which the wafer is converted to a cell. So if you see a wafer, it will be gray in color. So it is a simple uniform gray color surface. And after processing, the anti-reflection coating is done. This um, collection of hole and electron, then metal masking is done, and many other processing are done for making it a cell, and then it is encapsulated to make a module. Okay, and soldering is done for all the cells together in series. So that technology is highly matured now. There are many countries in the many companies in India, but they all import either wafer or cells. They are not manufacturing the wafers. The wafer is manufacturing a wafer itself is a long or energy intensive and costly process. Second generation is a thin film technology. Thin film technology do not make individual cells. It makes a complete module together. So it is a sheet kind of thing, which is thin, as the name suggests itself. Is it's around 20 to 30 micrometer thickness. However, this wafer-based technologies is of 200 to 300 nanometer thickness. So that you can imagine the thickness is quite low in thin film. That's why the name is a thin film. And the film means it can be flexible. It can be made as a roll. It is not necessary to be. How many of you have seen the solar PV module physically? Means physically means not in pictures. Just physically, have you touched it? Anyone?
Yes, sir.
So it is a glass, hard glass is there, the metal framing is there, right? But in thin film, actually, that kind of thin film is also available where the glass cover is there and the metal frame is there. But it can be also available in the form of flexible sheets like carpet. Okay, and it can be integrated with the building, so it can be fitted with the glass walls of the building. That's why it is called building integrated PV also. And the third technology is based on the this nanocrystal or organic desensitized dye-sensitized solar cell, but that technology is not commercially available in the market, and this is still under R&D level. And the major advantage, or major, you can say, the merit of the third generation technology is that it is made up of organic material. So it is expected that the environmental impurities are not too much high. But the major problem with those things is life is not that good as we have with the silicon based or thin film based solar cells. Okay, so still the first generation is dominant, and among this first generation, monocrystalline and polycrystalline are the two major category. Monocrystalline means it is made up of a single crystal, so the grain boundaries are minimal, and crystal, you know the definition, all the lattice are structured properly. So efficiency is very high. Polycrystalline has less efficiency, but has a low cost because it is multicrystalline. Single crystalline process is little costlier, and this second generation thin film can use cadmium telluride or amorphous silicon as the material. These material actually, the objective of this material is based on the efficiency, maximum efficiency, which of the photons falling on the from the solar radiation on the solar cell, which provides the highest band gap energy. So corresponding to that photon energy, which material gives the highest efficiency while absorbing the energy from those photons. So there are various, what you say, the heterojunction modules are also there, where one compound is there on the one side of the junction, other compound is there on the other side of the junction, and that's how it has the ability to absorb more or different frequency or different energy of the photons. Right. So let's say the efficiency of the photon falling on the cell is around 1.2 electron volt. Now that band gap energy of that material on which it is falling is, let's say, 1 electron volt. So what will happen? So the falling photon is 1.2 electron volt. So it will absorb 1 electron volt, and it will go the next state. The electron and hole pair will be liberated and they will move across the junction. But that remaining zero point 0.2 electron volt is gone wasted. Okay, so that is the reason that if you have another material which has a different band gap energy, then it can absorb more photons, right? Or wider, if wider energy photons can be absorbed. So overall efficiency will be more. If you can capture more photons with wider energy band gap, the efficiency of the solar photovoltaic material will be more. And that is the reason that different materials are being research is being made to find the maximum efficiency during this photon absorption. Till now, in the commercial scale, this first generation is giving maximum efficiency is around 16 to 20%. Thin film material has a very thin layer of this material. That's why the amount of photon absorption reduces, right? But the process is such that individual cells are not need to be manufactured. So the processing time, processing expenses are less. So it is less costly, but efficiency is also less. However, the first generation is more energy intensive process and more costly process also, but the efficiency is higher. It is around 16 to 20%, but the thin film is around varies from 12 to 15%. Third generation is still at the R&D level, so those levels are changing as when a new invention is made. Any question here? So all of you please read or go through those NPTEL lectures. You'll get more understanding of these things, because this solar PV technology is evolving over the last several years, and many new things are being added. But till now, this classification is still maintained: first generation, second generation, third generation. Now there is a lot of geometry is involved with the solar PV panel, right? Whenever you, yeah, bolo.
Sir, what you told about that wastage of some energy, I didn't get that point.
So
In
what
previous
happened?
slide.
Yeah, what happened like in this figure, solar radiation is falling on the panel, right? So what is solar radiation? Solar radiation is nothing but the photons, right? Hello?
Yes, sir. Yes, sir.
Yeah. So photon energy, the energy of the photon should be more than the band gap energy on the material on which it is falling. Then only the electron hole pair will generate.
Yes, sir.
Right? So that is the basic concept. So the photon
Oh,
energy should be greater than equal to the band gap energy of the material on which it is falling. Then only the electron and hole pair will generate. To liberate the electron, the photon energy should be higher than that. Now, every material has a different photon energy, right? And that leads to the research or development in the different materials. The material may be a single material, it may be a compound material, it may be different material across the junction, PN junction. So material wise, it is same PN junction material, p type, n type. but the material may be different on p type and n type, so that different energy of photons can be absorbed. So there is a one variety of solar cell is called tandem cell, or you can say the cascaded cell. So it is a layer of two or three different type of materials, and each one will be of having different band gap energy. Okay, so
Okay,
what will
sir. Got.
happen? What will happen? What you will? How will you arrange them? Suppose the top, the one material A is having 1.5 electron volt. Material B is having 1.3 electron volt, and material C is having 1 electron volt. 1.3, 1.5 electron volt. A, B, C. Right? Suppose you have to put them, or you have to make a cascading of these three. What should be your order on the from the
So
top? Sun
laser band gap
rays
should
are
be
coming
at
from
the
the
top.
top. Yeah. Which one?
So laser band gap should be in the top, and
Lesser
higher band gap
bandgap
should
at
be
the
at the,
top. And why?
because that bottom one should be higher because of the energy of light will be reach there very little. And
Any other question answer? Could you understood my
Sir,
question?
opposite.
I have three materials A, B, C. Material A has a band gap energy of 1.5, B has 1.3, C has 1 electron volt. Light is falling from the top. Which one you will put from the top? A, B, C or C, B, A?
Sir, with 1.5 electron volt on top.
Your answer is reverse. Why?
Sir, because top will get most of the sunlight and it may easily, electrons may easily come out.
Electrons will
There may be
easily
high.
come out.
They may get higher energy.
So if the suppose the photons of
I mean, sir,
1 electron volt
most of
no
the photons will fall on the top. So
so what will be passed through from A or from the top layer? After passing through the top layer, what electron volt will pass through?
less than 1.5 volt.
Right. So that is the reason. If you put 1 electron volt at the top, it will only pass through less than 1 electron volt to the next one. Right? Hello? Can you hear
Yes, sir.
me?
Yes, sir.
Hmm. So if you put 1.5 at the top, then what will happen? Less than 1.5 will not able to absorb by that top layer. So it will be absorbed by the second layer, which will have 1.3. Then whatever less than 1.3 will go to the down one, which is 1 electron volt. So it will be longer, or the you can say the larger photon number of photons can be absorbed with this cascaded effect. But those technologies are costly and they are still not commercially very attractive. So that is one side. Now coming to this figure, it is also important to understand this geometry, solar geometry. It is called solar geometry. Solar geometry involves a lot of angles. So you can see zenith angle, right? Zenith angle is the angle between the sun ray and the zenith at that location. So this blue color panel is a solar panel. Then beta is the tilt angle. So it has to be tilted with respect to the ground surface. Then solar azimuth angle is the angle of the ground surface with respect to the due south. We You have to understand the solar geometry first of all. Have you ever seen the solar trajectory or solar path? Solar on a daily basis, what is the trajectory of the sun? East to west, right?
Yes, sir.
Okay, and it will remain between this half quarter, this zenith and the south in between. It will not go to the full north to south, right? That the this angle, the zenith angle, changes with respect to the season, right? So in the summertime, this zenith angle is lesser. In the winter time, zenith angle is more, right? In the summertime, the sun is almost overhead, but in winter time, sun is having more zenith angle. So the sun trajectory is like semicircles, and which is a different angle from the zenith depending upon the season. So the sun tracking, there are sun tracking system. So one solar panel or an array of solar panel can be placed on that sun tracking system, and they will track or they will move actually as the sun moves. So they will follow the sun path. That is called the solar tracking system. We have installed in our campus at the JC Bose Lab Complex rooftop both dual axis sun tracking system as well as the single axis sun tracking system. Single axis is only east to west on daily basis, and dual axis is also follow this seasonal variation. Okay, so it has a both azimuth angle and altitude angle variation both. So there are two stepper motors, and in single axis tracking there is only one single stepper motor which goes from east to west. So what is the point of doing all this solar geometry? Why we need this? The point here is the location or the solar radiation falling on a particular point on a day at a particular time has to be calculated, has to be accurately estimated. And for that, all these angles, not only these angles, there are many other angles I have not shown here, has to be incorporated, and there is a model, mathematical model to calculate that. So if solar radiance is I at particular time at particular location, the solar radiance coming on a place is called I cos theta, where theta is the angle of incidence. Now that theta angle or cos theta depends upon various angles mathematical relation. So that is a long formula which depends upon many gamma, beta, theta, z and all that. And that includes the not only these angles, that includes the day of the year, and that includes the time of the day also. So the solar angle is also involved. The declination angle is also involved. Declination angle changes with every day location, nth day of the year. So all those factors are involved. So at a particular day, at a particular time, what is the incidence angle that can be calculated? And this drawing is correlated to that, but I am not showing all those formula and correlation here. I'm just giving an idea. If you go to that book, the whole mathematical derivation and formulation is given, cos theta for solar incidence angle. Okay, let's move on to the next. This is showing the working principle and electrical equivalent circuit of the solar PV cell. Right. If we talk about a single basic unit, it is a cell. When these cells are interconnected in series, it makes a module, one panel, one metal encapsulated panel is called a one module. Now, when these modules are interconnected in a combination of series and parallel, it becomes an array. Right. So the first picture from which I have started, it is showing an array. Right. So this is one module. This aluminum white color boundary is one modules, and this within that there are rectangles. You see. Can you see my mouse?
Yes,
Hello?
yes, sir. Yes, sir.
Yeah. So this one particular rectangle is a cell. Within one rectangle, there are three white lines are also there, narrow white lines, thin. So these are the silver lines. They are used to collect the electrons. Right? There are horizontal and there are vertical lines also. There are much thinner horizontal lines are there, and over them this vertical lines are there, which are little thicker. And so this rectangle is one cell. So if you count, there are 72 cells. They all are series connected, and that makes one module. Then series parallel combination of these modules makes one array. So this whole picture is one array. Okay. Okay, now as I've told you, this is a PN junction diode, and you can see there is a P-type silicon and there is a P-type material. Both phosphorus and boron are shown here, positive and negative. And above that there is a processing of anti-reflection coating is done. Then these electrodes are there, and then for connection, and then the back electrode is there for positive terminal, and this electron is flow in the reverse direction of the current when the sunlight falls on it. So these dotted 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 red lines are showing the photons are falling sunlight. Now these photons, it's not necessary that whatever is falling being utilized here. Almost 50% photons go waste. Only less than 50%, around 49.5% photons are useful. Why waste? Because you can see one arrow is showing reflected back. So it's not that it will be, if it is falling, it is will absorb. It can reflect back also. After that, if it is absorbed, it is not necessary that it will generate the electron hole pair. It can pass through. The one arrow is going out of it without doing any useful work. Then there may be some who can be used or generate the electron and hole pair. Now, even after generating electron and hole pair, there may be some recombination may happen. So ultimately, final is less than 50%, which is used to generate the electron and hole pair. Now, if you remember the definition of current source and voltage source, so it gives a characteristic of a current source, DC current source. So that's why it is represented by a IL current source. Okay, and then there is a physical diode which behaves like a diode definitely, which is be actually as a anti-parallel with respect to this source, or you can say the forward biased basically with respect to the source direction. So it is shown as a forward bias with respect to the source. Then there is a some losses involved which are reflected through the represented through the series resistance and shunt resistance, which is RSH is the shunt resistance, RS is the series resistance. The series resistance is basically providing this electrode loss or metal contact loss and all this, and leakage resistance is represented by this RSH. Okay, so this is the electrical equivalent circuit. IL is the source current or photovoltaic current, ID is the diode current, ISH is the shunt resistance current, I is the load current, and V is the terminal voltage, cell voltage. Okay, and this is related to this equation. So the current which is coming to the load or I, output current, is IL source current minus diode current. Diode current is equal to I naught times e to the power V plus IRS and Vt minus 1. So I naught is the reverse saturation current. So this whole thing I naught times e to the power this is basically ID. Okay, diode current. Then minus the shunt resistance current, which is V plus IRS in divided by RSH. So this is the electrical equivalent model circuit and the model for this solar PV cell. This representation of ID with this I naught is known to you, where D is the ideality factor and Vt is the thermal voltage. Any question here? I hope my audio and video is properly in synchronism. Rashmita, are you following?
Yes, sir.
Is going well?
Yes, sir. It's
Okay, good. Any question from student side?
Sir, from where is the shunt resistance is rising?
Shunt resistance is coming because of the leakage happening. So there is a drop in the voltage also, and that is being represented by the shunt resistance. 1 minute. So I have changed this video. Rashmita, you please cross check and let me know. Huh?
okay, sir.
And this mail has also been sent to all of you. If anybody has not received the mail, let me know. I've just now sent a mail, last mail to all of you through ERP. Please check it once and let me know if you have not yet received. So this is the basic brief introduction, and all of you please go to those NPTEL lectures in the book and have a detailed review of this. Now this experiment is again to give you an understanding that how this solar PV system works. What are these basic characteristic? Basic means IV characteristic, current and voltage characteristic, and the working principle. And that characterization will be done through different study. What we do, we will vary the load in the first case under given artificial insolation. Then we will change the insolation under different insolation condition, and then we'll put the dark test also. So what do you think? Under the dark test, the behavior will be like the solar cell will be like the diode. Okay, so that is one of the case we will do. Okay, so now let us move on to the setup first. So this is the diagram of the system setup. We have a single phase supply through the switches we are giving to the bulb. These bulbs are ultraviolet artificial solar insolation lamp from around 300 watt each, and there are 16 total bulbs, and we have a solar photovoltaic panel. This panel is based on this first generation, that is monocrystalline solar PV cell, and then we are having some measurement switches load for this. So this diagram is zoomed here. So if you see from the switches S1, S2 which are connected across the load, then voltmeter, ammeter, then there is a panel, and panel is 35 watt and 20 volt ampere volt open circuit voltage, 2.4 ampere short circuit current, and we have this assembly of the all these lamps. Right, there are 16 lamps, and we can switch on and off them individually with the different switches on the board. Then single phase supply is connected to this lamp arrangement, and there are cooling fans are also there. Okay, so it's a simple setup, not very difficult to understand. Any question here? Okay, let me try the video this time. So this is the actual setup, actual photos of the setup. So if you start from the left hand side, ammeter, variable load, multimeter for voltmeter, switch S1, lux meter, switch S2, power supply, cooling fan, solar emulator, basically the solar lamp system arrangement, and the panel. So this panel and lamp arrangement is zoomed here in this box and dotted white border. So they are face to face, the panel and the solar lamps, not solar lamps, basically the artificial lamps, they are face to face. You can see 4 in each row. There are 4 rows, there are total 16 lamps. And this is a lamp specification. It's a 230 volt, 300 watt, 1.3 ampere UV lamp, ultraviolet. This is the dark test experiment when the panel will be covered with the cloth, black cloth. No light source will be provided to it. Only a open circuit voltage condition will be created, and this photovoltaic panel covered with the cloth is tested. This is the actual operation. The lamp will not be energized, and the panel will be closed, and the regulated voltage supply will be given. Okay, let me try the video. Experimental setup. Are you able to see that and listen it? I have paused it now.
So cannot
Rashmita,
listen.
can you see the video?
Yes, sir. Video is visible, but let's see whether it's audible or not.
Audio audible, not audible, sir.
Your audio was not coming.
Yes, not audible.
Sir, can you play it once? It is right now paused. No, sir, audio is not coming.
Okay. Okay, let me, what I do, I will speak here. Okay. So just see the video. I will speak now. I'm restarting it. So this is the experimental setup, and on which panel and various. This is the panel we are going to. Now, this panel is called here. So this panel you can see.
Sir, your voice is breaking.
Hello.
Yes, sir. Your voice is not audible.
My voice is not audible. When the
Sir,
video.
actually, when you are playing the video and at the same time when you are speaking, there is some, I think, bandwidth loss. So it's better you can pause it and you can speak at that time.
Fine. So this is the solar panel, one panel, and this is the one cell. So you can see there are 4 cells in each row, right? 4, 4, 4, 4 like this. So this is the old panel design where it is of low power rating, and you can see there are horizontal white lines on each panel, right? And these are actually metal masking. It is only to capture or the electrons which are liberated after this uh, photon falling on it. Then there is a perpendicular thick line on this which will further collect it from those horizontal lines, and these are further connecting one cell to other cell in series. So it is the whole lot is coming in this way. So you can see 1, 2, 3, 4, 5, 6, 7. Yeah. How many rows are there? 1, 2, 3, 4, 5, 6, 7. 7 fours are 28. So there are 28 cells here, right? And all are series connected. So there all are series connected, and the current will be remain same from each cell, almost equal, and the voltage will be add up. So if you remember, the voltage and current rating was given there before the experimental setup diagram. So this is emitter and the switch S1, which we have shown in the diagram. So that load, variable load, is connected to the panel directly. This multimeter will be used as a voltmeter. This voltmeter is connected through this variable load and the switch. Now this second switch is used to short circuit, and it is connected across this load. So it will provide the short circuit situation. So this is the lux meter, which will use to measure the artificial insulation falling on the panel. Actually, this is not the only lux meter. It can measure and other things also. Like at the top, you can see it is working as an anemometer also. So it can measure the wind speed also. Then there is a lux there. Then humidity sensor is also there, is mentioned there, and it can hold the data. And so it's a multifunctional. This is the only lux meter which we have used here because of the problem of the range which are supposed to measure here. You can see here the lux range is much higher compared to the previous meter. So we have actually used this meter. Now you can see actual number of cells. What I told you earlier was not correct. Now you can see the full panel. Here 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 for the 36. There are 36 cell in one module. So nowadays the module which is coming available in the market is of 72 cells. Okay, so you can imagine the size is also a little bigger. So this is the cooling fan because if you operate it for a little longer time, there is a huge heat is generated. So it's they are required to keep it normal temperature. These are the manually operating switches which we can use to on and off the lamps as required. So this is a supply which DC supply basically which will be used in the second part, dark test. Again, this is the actual DC power supply source which we will use in the experiment. So this is the overall setup, and there are few modules you can see which are lying in the ground, and these are very old modules. Very old means they are around more than I think 20 years old. So when I joined the department, they are available before that. So it's already 13 years for me to be here, and you can see there is a lot of space unused in a module surface. In this circular cell, you see a lot of space is unutilized in the module surface, right? So that was a wastage of space. And nowadays, after that, this module has come where you can see only a diamond shape area is wasted. Rest of the space is fully utilized by the cell in a module. So it is a better design, and further actually if you see there are one module where you will find almost in the initial picture of my PPT you will find no space left. Even this diamond shape white space is also not there. So this was all about this I think let me switch off my video, it will improve the things. Yeah, any question till here? All of you could follow the video? Hello?
Yes, sir, you are audible.
Could you follow the video? It was okay?
Yes, sir.
Yes, sir.
So why you people are so silent today? What happened? Busy with something else? Just log in here and doing something else? Should I call the name? What you have understood? So
Monday
Ishan,
is very
what you said?
Monday is a very hectic day for us, sir. Like we have been doing classes since today 8 a.m. in the morning.
घर में बैठे हो, घर का खाना खा रहे हो, क्या हैट्रिक क्या होता है? हाँ? इतना स्माइलिंग तुम्हारा वो है फोटो, प्रत्युष?
Yes, sir.
ये हैट्रिक का डेफिनेशन क्या है?
Hectic is like sir, 8 to 9.
8 to 9.
9 or 8. Sir.
अभी यहाँ से निकलने के बाद 1 साल बाद तुम कोई जॉब आएगा और वो बोलेगा 8 to 9 काम करो, तो क्या बोलोगे? नहीं करेंगे?
No, sir.
हाँ? वो भी घर में बैठ के नहीं कराएगा, अपने ऑफिस बुला के कराएगा। हैं? घर में तो जब चाहो लेट जाओ, जब चाहे खा लो, जब चाहे सो जाओ। अभी क्लास में तुम बैठ के कर रहे हो कि लेट के कर रहे हो, डजंट मैटर, nobody will ask. So this whatever you people are having, this is a training program. You are getting trained for become a professional. So ये सब तो ट्रेनिंग का पार्ट है, हैट्रिक। ओके, ये असाइनमेंट, ये टेस्ट, ये experiment, these are all designed to make you people fit in the professional field. That's why the companies come to IIT system. Why they prefer IIT student? Simple logic is that that kind of efforts or that kind of labor, hard work is not done by students in other colleges. So they believe in the system, that IIT system will make you people strong enough that you can easily sustain in any harsh environment of industrial work. Okay, so don't make yourself soft and very fragile kind of thing. Okay, make yourself strong enough. अभी तो घर में रह रहे हो, घर का खाना पीना खा रहे हो, फिर कैसा प्रॉब्लम? आज सब लोग ढीले हो, क्या बात है? Nobody is responding. अच्छा, what you will feel? Suppose I also say like कि मैं भी दिन सुबह आज बहुत मीटिंग था, आज मंडे मेरा भी बहुत हैट्रिक होता है, शाम को 6 बजे लैब क्लास ले रहा हूँ, वो भी 2 घंटे तक बोलता रहूंगा लगातार। मैं अगर सेम एनर्जी लेवल के साथ मैं बात करूं जैसे तुम बोल रहे हो, हाउ विल यू फील? हाउ विल यू टेक द क्लास? विल यू एंजॉय इट? नीतीश कुमार, नीतीश कुमार, देखो लॉगिन करके चला गया कहीं। नैन्सी अग्रवाल, लेखराज,
Yes, sir.
गुड मॉर्निंग, हाउ आर यू?
Fine, sir.
क्या बात है? कुछ क्वेश्चन नहीं, कुछ नहीं?
No, sir.
नहीं है, सब क्लियर? ये सब लोग कहाँ हैं? नीतीश कुमार, नैन्सी अग्रवाल, राहुल अग्रवाल,
एग्रीकल्चर।
राहुल अग्रवाल,
Yes, sir.
किसी और को बैठा के चले गए हो तुम?
No, sir.
हाँ, क्या हो रहा है, क्या कर रहे हो? Okay, let me take it forward. You enjoy. So let's see the video for the experimental number case 1, where we will vary the load, and the second case with the dark test. Okay. Uh, yes, case 1. Are you getting the audio now or only video?
Only videos.
Okay, so this is the case 1 when we will use this artificial insulation through these lamps, and we will vary the load so that we can get the voltage versus current or current versus voltage IV characteristic for the this panel. And after this, what we will do, we will try to calculate the RS and RSH from that curve. Okay, so that is the idea. So I will keep speaking in between. I will pause it and we will talk. So this is the format which will be used to record the data or result. We will use 4 lamps, then will 8 lamps, then 12 lamps, then 16 lamps, and the corresponding lux value is also known to us. So we will change the load, so the current voltage and the corresponding power will also vary. So this is the part 1 where with the 4 lamps only. So this is a situation of open circuit voltage, right? And this is showing the open circuit voltage because till now we have not given any load. So now we have connected the load with the switch S1 and we are increasing the load. So we will get some current. Earlier the current was 0 and the voltage will reduce now. So current is 0.15 ampere and the voltage is around 14 volt. So we are gradually increasing the load so that the current can increase and voltage is recorded accordingly. So rheostat is at maximum value. Now we can do the short circuit condition. So this is now 0.24 ampere is the short circuit current and voltage is almost 0. So this is the first set of data with 4 lamps. Similarly, we get the data for 8 lamps and 12 lamps and 16 lamps. All of you are able to see the video properly?
Yes, sir.
Yes,
Anyone has any problem in watching this video? Okay. Now middle two rows, 4 plus 4, 8 lamps are on. So we will do the same process with this arrangement. So with this 8 lamps, it is around 3000 lux. No, sorry, 30,000 lux. 300 into 100. So similar result has been obtained with the 8 lamps. You can see the 4 lamps and 8 lamps, and the same setup will be repeated for the 12 lamps and 16 lamps. So this was about the load variation, and these are the lux values which we have recorded for different number of lamps, and these are the voltage and currents. You can see that the experiment was started with the open circuit condition, the open circuit voltage, and then the short circuit current is reached at the bottom. It is not visible here. Yeah, ISC is achieved in all the cases, and you can see that ISC value is increasing. So with the 4 lamp, 10 lamp, 12 lamp, 16 lamp, you can see the ISC value is increasing, right? And that is the reason that the happens in the real solar cell also, and the real solar insolation also. And as the solar insolation is more, the current is more, proportionally almost increases with the increase in the solar insolation. But open circuit voltage remains more or less same, so that is not changing. And the corresponding Vm and Im, Vn and Im are the maximum voltage and current. Maximum means the voltage and current maximum at which the power is maximum, right? It is not the individual value of their maximum. You can see the voltage maximum is around 12, 14, 14.8, or you can say 16.4, but it is the point of product of these two is maximum. So that is called the maximum voltage and maximum current, which basically where the power is maximum. So with these four tests, we have made it four characteristic, and the top one is with the 16 lamps, so it is giving the maximum current. You can see the open circuit voltage is converging to the same value. So this is called the IV characteristic, and the power value is increasing as more and more number of lamps are connected with the voltage. This is called the IV characteristics. So from this characteristic, we can find the values of RS and RSH, which we have used in the equivalent circuit model. Dark test 2, case 2 is shown here. Let me show the video of this also. All of you are following it? Any problem? Any question? So this panel is connected to this regulated DC power supply, and there is no lamp is on. So it is a dark condition. No insulation is available. Panel are covered with a dark cloth, so no tube light or no kind of light is coming on the solar panel, right? And then we are applying a voltage to the panel. So basically we are trying to get the diode characteristic. So it is that module is basically inherently a diode. So we are doing or getting a diode characteristic from this test. So we are slowly increasing the input voltage and we are measuring the recording the current correspondingly. So this is the table for the dark test which we have measured in this case. Now, when we will plot it, it will look like a diode curve. So that was the dark test, and this is the result of the dark test, and the curve will look like a diode curve. Okay. Now, if you remember the equation which we have used for the, you please remember this profile of the curve, right? The what we have just received as a dark curve. Are you able to hear me?
Yes, sir.
Yes, sir.
Rashmita, have you checked that video is correctly uploaded now?
Yes, sir. Yes, sir. It's fine now.
Okay, good. So yes, this one. This equation I is equal to IL minus this ID. I naught times this. It is ID minus this. Okay, let's forget about the last component because let's we neglect RS and RSH. So what is I? I is IL minus ID. Now IL is supposed to be, let's say, the constant. Okay, at a given solar insolation, the IL is constant. So IL is a horizontal DC line, DC current. ID curve we have just seen. It is rising exponentially after certain value. Right now it is minus ID. So you just reverse it, make it minus ID. So it will go just mirror image with the y-axis, right? Okay, got it? So minus ID will be the mirror image of the curve which we have just obtained from the dark characteristic towards the y-axis, minus ID. Now you add in minus ID this IL. So it's a DC shift to the minus ID, right? So the DC shift to the minus ID and will give you this curve which we have obtained here. So it was like this, negative of this is like this, going downward. Then addition to this will be DC shift addition will lift it upward and will like this. So that is that is how we get this IV characteristic in the solar insulated condition or illuminated condition from here. Is it clear to everyone? Why the profile of IV characteristic in the case 1 is like that? So that is minus of this means downward in negative direction, where mirror image in y-axis, and then DC shift uplifted by a constant value. So this minus this will downward and this plus this constant value will come like this. And that's how these are the two cases we do, and this is the overall results which we have obtained. Yeah, here we have to understand few factors. One of them is called the fill factor. Fill factor is different from efficiency. First of all, you should understand efficiency is as we define the efficiency, output upon input. But fill factor is the ratio of the power, maximum power, Vm into Im divided by VOC into ISC. Right. So Vm into Im happens to be at the knee point of this curve, where the product of voltage and current is maximum. That is called the maximum voltage, maximum current, divided by this ISC at the short circuit and VOC as the open circuit. So basically, if you make a rectangle with extending this ISC value and VOC value, you will get a rectangle, and you make another rectangle which will be smaller, making this from Vm and Im towards the x-axis and y-axis. So it is the ratio of these two rectangle areas is called a fill factor. So that means the how much fill or how much area you are filling out of the maximum possible area. Maximum possible area is Vm into Im. So crystalline cell has a very high fill factor, more than 70%, and that is how the fill factor is defined. But it is different from the efficiency. Efficiency is the output upon input. Output is the electrical power output from the solar panel. Input is the solar insolation which is falling on it. And RS and RSH are actually nothing but the slope defined at the ISC and the VOC side. so which is also written here, and then RSH is quite high compared to the RS value, and these are the insolation values which we have used. I think somewhere we have mentioned 8 lamps, but that was wrong. It is 10 lamps which has been used in the second case, then 12, then 16. So it can be concluded that case 1, by varying the load connected to the PV panel, IV characteristics is observed with the varying insolation, and approximate trajectory of the maximum power point with the respect to the changing insolation is also observed. Dark test is performed in case 2, and the characteristic of solar panel is studied by varying the load in different intensity of the light and zero intensity of the light to study the dark characteristic of the panel. Now, these are the questions which you have to answer while submission of the report in the discussion part. What is the impact of band gap energy on the efficiency of a solar cell? So I have given you a hint discussion on this band gap energy and solar cell efficiency has a relation. You please go to the chapter. It is discussed properly there. Generic and accurate equivalent circuit for a solar PV cell. So equivalent circuit we have already seen, that is generic and accurate itself with the equation of current and voltage, that is also given. Also explain the significance of all 4 components represented in the circuit. So IL, ID, RS, RSH, all those has to be, you just go through the chapter, you can follow it up. Sorry, what is the significance of fill factor? Just now I have discussed. What is the difference between efficiency and the fill factor of a solar cell? What is the impact of ambient temperature and solar insolation on solar PV performance? Yes. So I will give you a brief on this. You will find in detail on the chapter again. There are various characteristics are also explained. So the effect is reverse. First of all, the effect of solar insolation is proportional. Proportional means with the increase in solar insolation, solar cell performance increases because your input energy increases. Solar insolation is your input energy, right? So if you get more solar insolation, better solar insolation, your output will be better. There is no minimum or maximum solar insolation like minimum wind speed or cut-in wind speed in the wind system, but there is no minimum maximum here. So as higher solar insolation, your performance will be better or your current will be better basically. And that is one aspect. The temperature aspect is reverse. Higher temperature reduces the performance, and the higher temperature reduces the voltage actually, and increases the current but very slightly, very less, but reduces the voltage more. But solar insolation has a direct and proportional effect. So please again go to the chapters. You can see the impact of ambient temperature. How does it impact the IV characteristic? Similarly, the solar cell IV characteristic with respect to change in solar insolation. Then there are 2 different types of diodes are used. One is called a bypass diode and it is called a blocking diode. Right. So bypass diode are actually used to bypass a cell, which helps to reduce the effect under the shading condition. Suppose some of the cell or one of the cell is got shaded, then it will reduce the performance of the whole string or maybe the whole module. Right. So to reduce that effect, the bypass diodes are used, and blocking diodes, as the name suggests, block. But what it block? It blocks the reverse current. So in a string of modules, there may be a blocking diode so that the reverse current to the module is protected. So there are different purposes, different way they are connected. So again, this is explained in that book chapter. You go through it and find a detailed answer. So you have to prepare the report with the objective, experimental setup, you explain in your own words. Cases, you explain in your own words, and the results that you have obtained, analyze it, and you answer these 5 questions which are listed in the discussion part. And similarly to the previous report, you have to submit a handwritten report with all the plots handwritten, handmade. And this is a PDF file name in single PDF file. And each page you have to write on your own name with the black pen, bold letters, and submit it on the Moodle by 10th of February. Not 10th of February, sorry. We will get it by what today is 8th. So When we are supposed to submit it?
15th, sir.
15.
Sir,
10th,
16.
16. Chalo, one day we will reduce one day, 16. So 16th February by evening, okay? And please do not request that sir last moment मेरा नेटवर्क खराब हो गया, मेरा ड्राफ्ट सबमिट रह गया, मेरा ये हो गया, मेरा वो हो गया, मैं ईमेल से भेज रहा हूँ. Your email will not help me anything. I cannot upload your report, first of all. Second, your record will be lost somewhere. We have to manage 99 reports or whatever reports are submitted. So it will be very difficult for us to track it through email. So don't send with email. I am requesting again and again. Okay, sending by email is equally good as no submission. We will not entertain any submission through email. And you have been given enough time with proper announcement, proper timing. So please do it as early as possible without waiting for the last day, last hour. Okay, please do it on time, well before. And if you have any question, please ask. So Rashmita, are you following?
Yes, sir.
Yes, any question from student side? Hello? Yes.
Sir, I have question regarding
Bolo, bolo.
one student, that Vipul Tomar.
हाँ बोलो.
Sir, his roll number I'm not getting.
Vipul is here. Vipul, are you hearing me? Vipul Tomar. You are not getting his roll number.
Yes, sir. In the attendance list, I am not getting him because I am simultaneously I have taken the attendance, and few are absent here. But I got two students whose name is not there in the list, but they are here. So I doubt who are they. So that's why I just asked.
Others roll number is there?
Yes, sir. Yes, sir. Rest all are there. One more student was there, some Brahma, Japungshar Brahma. These two students are not having roll number here, but they are attending, means they are
No,
logged in,
no,
right?
they do not have roll number here. Means what about their roll list? Are they available in the roll list?
No, sir. That is what I'm saying. In the roll list, their name or roll number is not there.
Oh. Vipul Tomar.
Hello.
Yeah.
Hello, sir. I'm Vipul.
What is
Yeah,
the roll
Vipul.
number?
Who is speaking? Vipul Tomar?
Yes, sir. Am I audible?
Yeah, bolo.
Yeah, sir. She said about the roll number. So my roll number is 17EE10054. Should I write it down in the chat?
17
It's okay.
10054.
Yes, sir.
Okay.
Rashmita, his name is there in the roll list.
Okay. So that student roll list that you have provided in that Excel sheet, I am maintaining that attendance. So that's why I asked.
See, Shekhar has shared a Google Meet link.
Okay, sir.
One for attendance, one for maintaining the grades.
Okay, sir.
Are you following that?
No, sir. I just got this Excel sheet in which all the students' name
No.
list. Okay, sir.
No.
I will go through that Google sheet.
Please talk to Shekhar. I have
Okay, sir.
updated everything with him. I am not updating to each one of you separately because
Okay, sir.
Shekhar
Okay,
is
sir.
responsible to maintain these records, and number of students is large, so it's better that only one should maintain it.
Okay, sir.
Otherwise, it will mix